A bizarre comet from another star, 3I Atlas, is racing through our solar system, but just as Western telescopes went dark, China dropped a bombshell sharing incredible new images. This isn't just about a comet, it's about who controls the future of space discovery. Join our mission beyond the edge of the solar system. Subscribe now, and together we'll uncover the truth behind 3I Atlas, before it disappears forever. To understand the story of the cosmic stranger known as Comet 3I Atlas, we must first journey to the very edge of our own cosmic neighbourhood. Our solar system is a vast place, filled with planets, moons, asteroids and comets that have been circling our sun for billions of years. They're all part of the same family, born from the same cloud of gas and dust. They are familiar to us, like neighbours we have known our entire lives. We understand their habits, their composition and their history. But sometimes, a visitor arrives from far, far away. This is what makes 3I Atlas so incredibly special. It is not one of ours. It is an interstellar object, a traveller from a completely different star system. Imagine our solar system is a small, quiet island in the middle of a vast ocean. All the birds and animals on our island are related to each other. We study them and know their family trees. Then one day, a strange, colourful bird with feathers we have never seen before lands on our shore. It didn't hatch here. It flew across the enormous ocean from another island, an island we have never visited and know nothing about. This bird is a messenger, carrying with it the secrets of its distant home. Comet 3I Atlas is just like that bird. It is a physical piece of another star's family delivered directly to our doorstep. It offers a rare chance to study the building blocks of a planetary system that is not our own, giving us clues about how stars and planets form elsewhere in the galaxy. This makes the comet a priceless scientific treasure. Instead of pointing our powerful telescopes at distant stars hundreds or thousands of light years away, trying to guess what their planets are made of, here we have a sample that has come to us. It is a tangible piece of another world, a cosmic artifact that has journeyed for perhaps millions of years through the cold, empty space between stars. The materials frozen within its icy body are a time capsule from its birthplace. By studying its chemical makeup, we can learn about the conditions around its home star. Was that star system rich in the same elements as ours? Did it have different ingredients that could lead to different kinds of planets? These are the fundamental questions that drive astronomers, and 3I Atlas holds the potential to answer them. The discovery of such objects is a very new field of science, made possible only by our increasingly powerful telescopes that scan the sky every night. We live in a golden age of astronomy, where we can detect these faint, fast-moving visitors. The name 3I itself tells a story of rarity. The I stands for interstellar, confirming its origin from beyond our sun's influence. The 3 means it is only the third such object we have ever confirmed in all of human history. This number alone highlights the profound significance of its arrival. We are not dealing with a common occurrence. This is a once-in-a-decade, or perhaps even a once-in-a-generation, event. Each interstellar visitor provides a unique data point in our quest to understand the universe. The first confirmed interstellar object discovered in 2017 was named Oumuamua. It was a complete mystery, a small, dark and elongated object that tumbled strangely through our solar system. Scientists were baffled by its behaviour, and it sped away before we could get a good look. We were caught by surprise, unprepared for such a visitor. The second, 2I Borisov, found in 2019, was more familiar. It looked and acted much like the comets from our own solar system, with a visible fuzzy head and a tail of gas and dust. It was a comforting discovery, suggesting that other star systems might form comets in a similar way to ours. It was a piece of another island that looked quite a bit like a piece of our own. Now, we have 3I Atlas. As the third confirmed visitor, it provides a crucial point of comparison. Is it strange like Oumuamua, or more familiar like Borisov, or is it something entirely new? The answer seems to be that it is unique in its own way, carrying a chemical signature unlike anything we have seen before. This makes it incredibly valuable. If you only have one data point, you know nothing. With 2, you can draw a line, but with 3, you can start to see a pattern, or the beginning of a much more complex picture. 3I Atlas helps us understand the diversity of objects that wander the galaxy. It tells us that the universe of small, icy bodies is likely far more varied and interesting than we ever imagined. One of the most challenging aspects of studying 3I Atlas is its incredible speed. It is not leisurely strolling through our solar system, it is rocketing through it like a cosmic bullet. Objects born within our solar system are gravitationally bound to the Sun. They travel in long looping orbits, like a tetherball swinging around a pole. Even long-period comets that visit from the edge of our system eventually slow down and turn back. But 3I Atlas is not tied to our Sun. It is travelling on what scientists call a hyperbolic trajectory. This is a fancy way of saying it is on a one-way trip. It is moving so fast that our Sun's gravity can't capture it. It will bend its path slightly as it passes by, but then it will fling back out into the interstellar void, never to return. This incredible velocity creates a race against time for astronomers. Our window to observe this object is short and unforgiving. Think of it like being a wildlife photographer trying to take a picture of an extremely rare bird that flies past your window at hundreds of miles per hour. You have only a few moments to focus your camera, adjust your settings, and capture as many clear images as you can before it vanishes forever over the horizon. Every second counts. Every piece of data collected is precious, because once 3I Atlas is gone, the opportunity is lost for all time. This urgency is what drives observatories around the world to drop what they are doing and point their most powerful instruments at this fleeting target. The final piece of the initial puzzle surrounding 3I Atlas is its deeply strange nature. Early observations quickly revealed that this was not a standard issue comet. Comets are often called dirty snowballs because they are primarily made of water ice mixed with dust and rock. As they get closer to the Sun, the heat causes the ice to turn directly into gas, a process called sublimation. This gas creates a glowing cloud around the comet's solid core, known as a coma, and gets pushed back by the solar wind to form a beautiful tail. We expect comets from our own solar system to be rich in water. It is their defining characteristic, the fuel that powers their brilliant displays. But 3I Atlas is different. It is weird. Scientists analysing the light coming from its coma found something peculiar in its chemical fingerprint. The ingredients were not what they expected. The balance of different frozen gases and materials was unlike that of the thousands of comets we have studied from our own cosmic backyard. This weirdness is what makes it so profoundly exciting. It is a genuine alien, not in the sense of a creature, but in the sense of its fundamental chemistry. It was born in a different environment, under different conditions, and its composition reflects that alien heritage. It is a chemical puzzle box that has travelled across the stars, and astronomers were just beginning to figure out how to open it, when our story takes its dramatic turn. The strange ingredients of this cosmic stranger held the key to its past, and scientists were eager to uncover its secrets. To truly understand what makes Comet 3I Atlas a celestial object of such intense interest, we must look closer at its chemical makeup, its list of strange ingredients. When astronomers first began to analyse the light from this interstellar visitor, they focused on its coma. The coma is the fuzzy, glowing atmosphere that surrounds the solid nucleus, or heart, of a comet. This cloud of gas and dust is formed when the Sun's warmth heats the comet's surface, causing its frozen materials to turn directly into gas. By studying the light that passes through this coma, scientists can identify the specific types of molecules present, much like a detective analysing fingerprints left at a crime scene. The first major clue that 3I Atlas was unusual came from the discovery of a huge amount of carbon dioxide, or CO2. Carbon dioxide is a very common gas. It is the same gas that we exhale with every breath, the same gas that plants use for photosynthesis, and the same gas that gives fizzy drinks their bubbles. In the cold depths of space, carbon dioxide freezes into a solid, often called dry ice. Many comets in our own solar system contain some frozen carbon dioxide. However, in our local comets, water ice is almost always the star of the show. They are overwhelmingly made of frozen H2O, with CO2 being a minor secondary ingredient. They are like cakes made mostly of flour, with just a little bit of sugar. This is where 3I Atlas completely broke the mould. The initial observations showed that its coma was incredibly rich in carbon dioxide gas. In fact, there was significantly more CO2 being released than water vapour. This flipped the standard comet recipe completely on its head. It was as if we had discovered a cake that was made almost entirely of sugar, with only a tiny bit of flour. This was a stunning revelation. A comet dominated by carbon dioxide suggests it was formed in a very different part of its home star system than where our own comets were born. Water freezes at a relatively warm temperature, while carbon dioxide needs much colder conditions to turn into ice. The high CO2 content of 3I Atlas hints that it may have formed in an extremely cold, distant region around its parent star, a place where the chemistry was fundamentally different from the birthplace of our own comets in the Oort cloud or Kuiper belt. This discovery was like finding a biological specimen with a completely different internal structure than any known animal on Earth. It challenged the core assumptions astronomers had about how comets are built. The fact that this object had travelled from another star system made the finding even more profound. It wasn't just a local oddball, it was evidence that the processes of planet and comet formation could vary dramatically from one star system to another. The universe might be full of all sorts of comets, with wildly different chemical makeups, each telling a unique story about the environment in which it grew. This carbon dioxide heavy nature was the first major piece of the puzzle, a giant clue pointing to the comet's exotic origins and making it a top priority target for every major telescope on the planet. Beyond the surprising abundance of carbon dioxide, further analysis of the comet's coma revealed other mysterious materials. The light signature showed the presence of complex organic molecules. It is important to clarify what scientists mean by organic in this context. It does not mean the material came from living organisms. Instead, it refers to molecules that are based on carbon atoms, which are the fundamental building blocks of life as we know it. Finding such materials on a comet is not new. Many of our own comets contain them. However, the specific types and quantities of organic compounds on 3I Atlas, combined with its other strange properties, added another layer to the deepening mystery. This chemical puzzle was made even more complex by the presence of other frozen gases. Scientists detected compounds like carbon monoxide and nitrogen, but again, the ratios were all wrong compared to what we typically see. It was like listening to a familiar piece of music, but with all the notes rearranged into a new strange melody. Each new piece of data only deepened the sense that 3I Atlas was a truly alien object. It was a chemical time capsule from a distant, unknown stellar nursery, and its contents were unlike anything we had ever encountered before. Unravelling this complex chemical signature became the central goal for researchers. If they could figure out the exact recipe of this interstellar snowball, they could start to paint a picture of the star system it came from. Confirming these strange ingredients required the most powerful astronomical tool ever built by humanity, the James Webb Space Telescope, or JWST. While many ground-based telescopes can study comets, the JWST has a unique advantage. It orbits far out in space, away from the blurring effects of Earth's atmosphere. More importantly, it is designed to see the universe in infrared light. Infrared is a type of light that is invisible to our eyes, but is perfect for studying the chemistry of cold objects like comets. When molecules in the comet's coma are warmed by the sun, they glow brightly in specific wavelengths of infrared light. Each molecule, whether it's water, carbon dioxide, or a complex organic compound, has its own unique infrared fingerprint. The JWST acted as a cosmic detective, using its powerful spectrographs to capture these fingerprints with incredible precision. A spectrograph is an instrument that works like a prism, splitting light into its component colours or wavelengths. By analysing this spectrum of light from 3I Atlas, astronomers could definitively confirm the high levels of carbon dioxide and identify other molecules with a level of certainty that was impossible to achieve from the ground. The data from the JWST was the gold standard, the final word on the comet's bizarre composition. It provided a detailed, unambiguous cosmic fingerprint of this interstellar visitor. The information gathered by the JWST was crucial for several reasons. First, it confirmed that the initial, ground-based observations were correct. 3I Atlas was indeed a carbon dioxide-rich comet, a true outlier. Second, it provided a much more detailed list of ingredients, allowing scientists to build more accurate models of the comet's structure and origins. These models are like a chef trying to recreate a dish by knowing the exact amount of each ingredient used. With the JWST data, scientists could begin to work backward, trying to figure out what kind of stellar environment could produce such a strange object. The telescope's observations were a monumental step forward in our understanding, solidifying the comet's status as one of the most important astronomical targets of the decade. This detailed chemical analysis provided the baseline, the foundational knowledge that made what happened next so scientifically dramatic. But hold on, this story isn't just about cool comet pictures, it's about a bigger game being played out in the stars, and the questions it raises about who truly leads the quest for discovery. The initial chapter in the scientific investigation of 3I Atlas was written largely by a network of observatories spread across the globe, primarily operated by Western nations and international consortia. These powerful facilities represent the cutting edge of astronomical technology, the culmination of decades of investment, research, and engineering. When the alert went out about a new, fast-moving object with a potential interstellar origin, this global network immediately sprang into action. It was a well-oiled machine, designed for exactly this kind of rapid response astronomy. Telescopes in Hawaii, Chile, and space were all pointed toward the faint visitor, to gather as much information as possible before it disappeared. At the forefront of this effort were some of the most famous and capable telescopes ever built. The Hubble Space Telescope, orbiting high above the Earth since 1990, played a critical role. For over 3 decades, Hubble has been our sharpest eye on the universe, delivering stunning images and groundbreaking discoveries. Its position in space allows it to capture incredibly clear pictures, free from the distortion of Earth's atmosphere. Hubble was tasked with imaging 3I Atlas to study its shape, its brightness, and the structure of the dust and gas boiling off its surface. Its observations were essential for determining the comet's size and tracking its activity levels as it approached the Sun. Hubble provided the clear visual context for the more complex data being gathered by other instruments. Alongside Hubble, the new powerhouse of astronomy, the James Webb Space Telescope, was brought to bear on the target. As we have discussed, the JWST's ability to see in infrared light makes it uniquely suited for dissecting the chemical makeup of celestial objects. Its massive golden mirror and highly sensitive instruments allowed it to perform a detailed chemical analysis of the comet's coma. The JWST's contribution was not just about taking pictures, it was about understanding the fundamental building blocks of this alien object. Its data confirmed the strange carbon dioxide-dominated nature of the comet, providing the hard evidence that made 3I Atlas such a scientific sensation. The combined power of Hubble's sharp vision and JWST's chemical sniffing abilities gave the world its first deep understanding of this visitor from another star. While the space telescopes provided a unique vantage point, a host of powerful observatories on the ground were equally crucial to the early observation campaign. Among the most important of these were the facilities of the European Southern Observatory, or ESO, located in the high, dry Atacama Desert of Chile. This location offers some of the clearest skies on Earth, making it an ideal place for astronomy. ESO's flagship facility is the Very Large Telescope, aptly named the VLT. The VLT is not a single telescope, but an array of 4 massive 8.2-meter telescopes that can work together to create an instrument with the light-gathering power of a single 16-meter mirror. The VLT was used to take deep images and detailed spectra of 3I Atlas, complementing the work being done in space. Its large mirrors could collect light from the faint comet, allowing for rapid analysis of its changing brightness and composition. Another key player in this global network was the Gemini Observatory. The Gemini network consists of twin 8.1-meter telescopes, one located on Mauna Kea in Hawaii and the other in Chile. This strategic placement gives astronomers access to the entire sky, in both the northern and southern hemispheres. No matter where an object is in the sky, one of the Gemini telescopes can likely see it. This was vital for tracking 3I Atlas as its position changed. The Gemini telescopes are equipped with a versatile suite of instruments, allowing them to take high-resolution images and perform spectroscopic analysis across different wavelengths of light. Along with other major facilities like the Keck Observatory in Hawaii, this powerful ground-based network provided a continuous stream of data, tracking the comet day and night as the Earth turned. Together, these Western and international facilities worked in concert to build a comprehensive picture of 3I Atlas. Their initial efforts were incredibly successful. They took the crucial first pictures, establishing the comet's existence and plotting its path through our solar system with high precision. These early positional measurements were what allowed scientists to calculate its trajectory and confirm, with great confidence, that it was indeed an interstellar object. Without this rapid, precise tracking, its extraordinary origin might have remained in doubt. The network watched closely as the comet's activity began to ramp up, documenting how its coma grew and its brightness changed as it absorbed more energy from the sun. This continuous monitoring is essential for understanding the life cycle of a comet. Most importantly, these observatories performed the initial reconnaissance of the comet's composition. Using their powerful spectrographs, they were the first to detect the unusual chemical signature, the abundance of carbon dioxide that set 3I Atlas apart from its local cousins. This foundational work laid the groundwork for all subsequent research. It was their data that sparked the global scientific excitement and made the comet a top priority target. The early observations from this powerful interconnected system of Western-led observatories were what defined our initial understanding of the cosmic stranger. They established the key questions and mysteries that needed to be solved. They were painting a detailed portrait of a visitor from another star, a portrait that was becoming more fascinating with every new piece of information. They were at the height of their investigation, a critical moment when the comet's behaviour was expected to become even more dynamic and revealing. It was precisely at this moment of peak scientific interest that the story took an unexpected and deeply concerning turn. The world's most powerful eyes on the sky were about to go dark. Just as the scientific community was buzzing with excitement over Comet 3I Atlas, an unexpected and frustrating problem arose. At a moment when the comet was entering a critical phase of its journey, approaching its closest point to the Sun where its activity was expected to peak, many of the world's most powerful Western telescopes suddenly became unavailable. The continuous stream of high-quality data that had been building such a fascinating picture of the interstellar visitor slowed to a trickle, and then, in some key areas, stopped altogether. The West's eye on the sky, which had been so sharply focused on this rare object, had been forced to blink. This created a critical gap in our observation, a period of silence that left scientists feeling anxious and powerless. One of the primary reasons for this sudden silence was the simple, practical reality of maintaining incredibly complex machinery. Giant telescopes are not like the simple backyard instruments you can buy in a store. They are some of the most sophisticated and delicate pieces of technology ever created. They involve massive moving structures, precisely polished mirrors the size of a small building, and supercooled, highly sensitive electronic detectors. Like any high-performance machine, whether it's a Formula One race car or a space shuttle, they require regular planned maintenance to keep them operating at peak performance. This can involve anything from recoating the giant mirrors with a fresh layer of reflective aluminum to upgrading the computer systems that control them. These maintenance periods are scheduled months or even years in advance, and are absolutely essential for the long-term health of the observatory. It was a stroke of deeply unfortunate timing that several major facilities had pre-scheduled engineering and maintenance shutdowns that happened to coincide with this crucial period of the comet's passage. Think of it like the city's best hospital deciding to close its emergency room for renovations just as a major accident occurs on the nearby highway. The timing was not intentional, but the consequence was the same. A vital resource was unavailable precisely when it was needed most. Scientists could only watch the calendar, knowing that a priceless opportunity was slipping away while the tools they needed were being taken apart for a tune-up. This practical reality of instrumental upkeep was a major contributor to the growing observational gap. Another significant factor was the intense competition for time on these world-class telescopes. Access to facilities like the Hubble Space Telescope or the Very Large Telescope is one of the most sought-after resources in all of science. Astronomers from around the globe submit proposals, often years in advance, detailing the research they want to conduct. These proposals are then judged by a panel of experts who select only the very best and most promising projects. The result is that the schedule for these telescopes is packed solid, booked up every single night, months and years into the future. Every hour of observation time is precious and has been allocated to a specific scientific goal. When a sudden, transient event like the appearance of an interstellar comet occurs, it creates a dilemma. Astronomers can submit what are called target of opportunity proposals, which are designed to interrupt the regular schedule for urgent, time-sensitive observations. The discovery of 3I Atlas certainly qualified, and it was granted time on many instruments. However, this emergency time is limited. You cannot simply cancel all other approved science projects for weeks on end to stare at a single object, no matter how important it is. Other astronomers were waiting to study distant galaxies, search for exoplanets, or investigate black holes. Their science was also important and had been planned for years. Consequently, after an initial flurry of observations, the time allocated to 3i Atlas began to run out on some telescopes, as they had to return to their previously scheduled programs. This combination of planned maintenance and overbooked schedules created what astronomers began to call a dark spot in their coverage of the comet. It was a period of days, stretching into weeks, where none of the premier Western facilities were able to provide the kind of high-resolution imaging and detailed spectroscopic data that was so desperately needed. The continuous movie of the comet's evolution was suddenly missing a crucial sequence of frames right at the story's climax. This was a source of immense worry for scientists. Comets, especially as they near the Sun, are notoriously dynamic and unpredictable. They can change on a daily or even hourly basis. They might suddenly brighten, release a massive plume of dust and gas, or even break apart completely. Missing these events is not just about losing out on pretty pictures. It means losing fundamental data about the comet's internal structure and composition. It is like a doctor trying to diagnose a patient's illness, but being told they cannot run any tests for 2 weeks. By the time they can observe the patient again, the key symptoms might have passed, and the chance to understand the cause of the illness is gone forever. This is the fear that gripped the astronomical community. A unique, irreplaceable scientific subject was performing its most interesting behaviours, and the best instruments to record it were temporarily blind. This observational blackout set the stage for a dramatic and unexpected development from a new and powerful player in the world of astronomy. The silence from the West would not be the final word. Into this period of observational silence, a new set of images suddenly emerged from an unexpected source. During the critical window when many Western telescopes were offline or dedicated to other tasks, China's national observatories quietly and strategically released a series of new, high-quality images of Comet 3i Atlas. This was a bombshell moment for the astronomical community. While scientists in Europe and the Americas were lamenting the gap in their data, their colleagues in China had been diligently tracking the interstellar visitor with their own powerful, state-of-the-art facilities. The release of these images was a significant event, not just for the study of this particular comet, but for the entire landscape of global astronomy. The timing of this data release was either a remarkable coincidence or a masterfully executed strategic move. It came precisely when the global scientific community was most desperate for new information. The data gap created by the downtime of Western telescopes had generated a palpable sense of anxiety among researchers. They were missing a key part of the comet's story. China's release filled that void perfectly. It provided the missing frames in the movie, allowing the world to see what the comet had been doing during that period of relative darkness. This dramatic timing immediately focused the world's attention on China's growing capabilities in space science. It was a powerful demonstration that a new major player had arrived on the scene, ready and able to make critical contributions when others could not. It is important to emphasize that these were not blurry amateur-level pictures. The images released by the Purple Mountain Observatory and other Chinese facilities were of high scientific quality. They were captured using large aperture telescopes equipped with sensitive modern detectors. These are serious professional-grade observatories, built as part of China's massive long-term investment in fundamental scientific research. The images were sharp enough to reveal fine details in the comet's structure, and were accompanied by the necessary technical information, such as timestamps and filter details, that would allow other scientists to analyze them properly. This was not a casual snapshot. It was a deliberate contribution of valuable scientific data. This move was a clear and powerful statement about China's capabilities in the field of astronomy and space surveillance. For many decades, ground-based astronomy has been dominated by a handful of countries and international consortia, primarily in North America and Europe. They built the biggest telescopes, developed the most advanced instruments, and consequently led the majority of groundbreaking discoveries. China, while a major global power in many other areas, had historically been seen as a smaller contributor in this specific field. This event single-handedly challenged that perception. By providing crucial data on a high-profile, time-sensitive target, when the established leaders were unable to, China showcased its technical prowess and its strategic intent to become a leader in space discovery. It was a declaration that the nation's investment in science was paying off, and that the world would now have to look to the east for the latest news from the cosmos. The emergence of these images from China immediately changed the narrative around 3I Atlas. The story was no longer just about a strange comet from another star. It was now also about the changing dynamics of science on planet Earth. The focus shifted from purely astronomical questions to include geopolitical ones. Who has the best tools to watch the sky? Who gets to announce the next big discovery? And who controls the flow of information that shapes our understanding of the universe? The quiet release of a few astronomical images had suddenly become a significant event, with implications reaching far beyond the scientific study of a single comet. It signalled a shift in the global balance of scientific power. The Chinese observatories, by stepping into the breach, had done more than just provide valuable data. They had asserted their relevance and capability on a global stage. This was a moment of immense national pride for China, a validation of its long-term strategy to build a world-class scientific infrastructure. For the rest of the world, it was a wake-up call. It highlighted a new reality. The exploration of the cosmos was no longer the exclusive domain of a small club of Western nations. A new era of astronomy was dawning, one in which discovery could come from anywhere, and the map of scientific leadership was being actively redrawn. The new images of 3I Atlas were more than just data. They were a symbol of this profound and ongoing transformation in how humanity explores the final frontier. The new images of Comet 3I Atlas, released by Chinese observatories, were far more than just a symbolic gesture. They contained concrete scientific information that was immensely valuable to researchers around the world. These pictures provided a crucial, detailed look at the comet during a period of its journey when it was undergoing rapid and significant changes. By studying these images, astronomers could begin to fill in the blanks left by the temporary silence of other major telescopes. The data offered fresh clues about the comet's structure, activity, and behaviour, allowing the global scientific community to piece together a more complete and continuous story of this interstellar traveller. One of the most important features revealed in the Chinese pictures was a clear, high-resolution view of the comet's coma, the fuzzy cloud of gas and dust surrounding its nucleus. The shape and structure of a coma are not static. They change in response to the comet's rotation and the way gas and dust erupt from its surface. Detailed images can show jets or fans of material shooting out from specific active regions on the nucleus. These jets are like geysers on a frozen world, powered by the sublimation of ice as it is heated by the sun. Observing the shape and direction of these jets can tell astronomers a great deal about the comet itself. For example, it can help them determine how fast the nucleus is spinning and which parts of its surface are the most active. The Chinese images provided a sharp snapshot of this coma structure at a moment when no one else was getting a comparable view. This was scientifically vital. If the comet had experienced a sudden outburst, releasing a large amount of material, these images would be the only record of it. Such outbursts are incredibly important because they can excavate fresh material from beneath the comet's surface, giving scientists a brief glimpse of the pristine, untouched ices from its interior. Without the continuous monitoring provided by the Chinese telescopes, a key event like this could have been missed entirely, leaving a permanent hole in our understanding of the object's composition and evolution. The detailed view of the coma was the first major contribution of the new data. Furthermore, the images showed tantalizing hints of the comet's developing tail structures. Comets typically have two main types of tails, a dust tail and an ion tail. The dust tail is made of tiny solid particles like sand or smoke that are pushed away from the comet by the pressure of sunlight. This tail is often broad, curved, and appears yellowish-white because it reflects sunlight. The ion tail, on the other hand, is made of gases that have been electrically charged by the sun's ultraviolet radiation. This tail is pushed straight back from the comet by the solar wind, a stream of charged particles flowing from the sun. It often glows with a faint blue light. The shape, length, and brightness of these tails provide a wealth of information about the comet's makeup and its interaction with the solar environment. The images from China gave scientists a chance to see how these tails were forming and changing over time. Were they consistent with the comet's known carbon dioxide-rich composition? Did the structure of the tail reveal anything new about the size and type of dust particles being shed by the comet? These are the kinds of questions that astronomers could begin to answer by carefully analysing the newly available pictures. Because cometary tails can shift and change on a daily basis, having these images from the dark period was essential. They provided a critical link in the chain of observations, connecting the earlier data from Western telescopes with later observations that would be made once those facilities came back online. The immense value of this new information was amplified by its exclusivity. For that specific period in time, the Chinese data was the only game in town. In science, having a continuous, uninterrupted stream of data is often the key to making a breakthrough. It is the difference between watching a movie and looking at a few random snapshots. The snapshots might be interesting, but only the full movie tells you the complete story, showing how the characters and plot develop over time. The scientific story of 3I Atlas was developing quickly, and the Chinese observatories were the only ones filming the most dramatic scenes. This made their contribution indispensable. Any scientific paper written about the comet's behaviour during this period would have to reference and rely on the data they provided. This continuous view is especially critical for an object like an interstellar comet. Because 3I Atlas is on a one-way trip out of our solar system, we only get one chance to observe it. We cannot wait for it to come back around in a few years to fill in the gaps in our data. Every moment it is observable is a unique and fleeting opportunity. By filling a critical gap in the observation timeline, the Chinese images ensured that our one and only chance to study this object up close was as complete as possible. They helped to build a more robust and detailed scientific record of this alien visitor, allowing for a more comprehensive understanding of how it evolved as it journeyed through our solar system. The secrets unlocked by these images were a direct result of being in the right place, with the right tools at the right time. The study of comets is a frantic race against time, a scientific endeavour where every second and every snapshot counts. This is because comets are not static, unchanging balls of rock and ice. They are dynamic, evolving worlds that change dramatically as they make their journey through the solar system. A comet observed today can look significantly different from how it looked yesterday, and how it will look tomorrow. This is why continuous observation is not just a luxury, it is an absolute necessity for understanding these cosmic travellers. The situation with 3I Atlas, a fast-moving visitor on a one-time-only pass, made this race against time all the more urgent, and every new piece of data all the more precious. The engine of change for a comet is the sun. When a comet is far out in the cold, dark reaches of space, it is dormant and frozen, little more than an inert chunk of ice and dust. But as its orbit brings it into the inner solar system, the sun's powerful radiation begins to heat its surface. This is when the magic happens. The frozen gases trapped within the comet, like water, carbon dioxide and carbon monoxide, begin to sublimate, turning directly from a solid into a gas. This process is similar to how a block of dry ice produces a thick fog at room temperature. This escaping gas creates the comet's coma and tails, the very features that make it visible and beautiful to us on Earth. The rate at which this happens is not constant. It depends directly on the comet's distance from the sun. As the comet gets closer, the heating becomes more intense, and the release of gas and dust can increase exponentially. This means the comet's brightness, the size of its coma, and the length of its tails can change on a daily or even hourly basis. Scientists need to track these changes closely because they reveal the comet's fundamental properties. For example, by measuring how much gas is being produced at a certain distance from the sun, they can calculate the percentage of different ices within its nucleus. Observing how these activity levels fluctuate gives them clues about the comet's shape, rotation, and surface features. Imagine trying to understand a volcano by only looking at a single photograph of it. You might be able to tell that it is a volcano, but you would have no idea how active it is. Does it erupt every day, once a year, once a century? To understand its true nature, you would need to set up a camera and record it continuously, day after day, to capture its behaviour over time. Studying a comet is exactly like this. A single image is just one piece of the puzzle. A continuous series of images and data points allows scientists to build a complete story, a life history of the comet's journey. They can see how it wakes up as it approaches the sun and how it fades as it moves away again. This is why the gap in observations from Western telescopes was so concerning, and why the emergence of the Chinese images was so important. The period when the other telescopes were offline was precisely when 3i Atlas was getting closer to the Sun, and its activity was expected to be most volatile and interesting. It was like the most dramatic chapter of a book, and for a moment it seemed like all the pages had been torn out. The Chinese data helped to write those missing pages. It allowed scientists to connect the dots, to see the progression of the comet's activity without a major interruption. This continuous record is the holy grail for comet researchers. Because 3i Atlas is an interstellar object, the stakes were even higher. This was not a member of our solar system's family that would eventually return for another visit. It was a tourist passing through, and once it left, it would be gone forever, continuing its long journey into the void between the stars. We have exactly one chance to get this right. Every observation we make, every spectrum we take, every image we capture is a unique piece of an unrepeatable experiment. We cannot press a rewind button and watch it again. The data we collect during its brief passage is the only data humanity will ever have on this specific object. This sense of a singular, unrepeatable opportunity creates immense pressure on the astronomical community. It drives the need for global cooperation and coordination. The goal is to have as many telescopes as possible, all around the world, observing the object, to ensure 24/7 coverage. As the Earth rotates, a telescope in one location will lose sight of the comet as the Sun rises. At that point, another telescope in a different part of the world, where it is nighttime, must be ready to pick up the observation. This global relay race ensures that no important events are missed. The 3i Atlas event, with its unexpected data gap, highlighted both the importance of this continuous coverage and the potential fragility of the system we have in place to achieve it. Every new piece of data was precious because it was a permanent addition to our one and only biography of this alien world. In the world of science, discovery is a competitive and fast-paced endeavour. While the ultimate goal is to expand human knowledge, there is also a very real element of prestige and influence that comes with being the first to find, analyse, and interpret new information. The group of scientists who publish their findings first on a major discovery often gets to shape the story. They establish the initial framework for how the discovery is understood, they propose the first theories to explain it, and their work becomes the foundation upon which all future research is built. This is the power of early data, and in the case of 3i Atlas, China's timely release of new images put their scientific community in a powerful position. Think of a major archaeological discovery, like the unearthing of a new, unknown tomb. The team that first enters the tomb gets the first look at the artifacts inside. They are the ones who get to catalogue them, take the first photographs, and propose the initial theories about the person who was buried there. Their interpretation will dominate the headlines and shape the public and scientific understanding of the find for years to come. Other researchers will eventually get to study the artifacts, but they will be building upon, or reacting to, the work of that first team. The first team sets the agenda. This is analogous to what happens in astronomy when new data is released. By providing the only new, high-quality images of 3i Atlas during a critical period, Chinese scientists and institutions gained a significant head start. They had exclusive access to this information before anyone else in the world. This allowed them to begin their analysis immediately. They could measure the changes in the comet's coma, track the development of its tail, and compare these new features to the earlier data. This work takes time and careful effort. While the rest of the world was waiting for new data, the Chinese teams were already deep into the process of scientific analysis. This gave them the opportunity to be the first to write and submit scientific papers based on these new findings. This early access could directly lead to their scientists creating the first important models of the comet's behaviour during this phase. A scientific model is a computer simulation, or a set of mathematical equations that attempts to explain an observed phenomenon. For example, a model of 3i Atlas might try to simulate how its specific mix of ices would sublimate at its given distance from the Sun to produce the coma and jets seen in the images. The team that builds the first successful model that matches the observations often receives significant credit and recognition. China's exclusive data gave them a unique advantage in this race to model and explain the comet's strange activities. This accomplishment provides a major boost to the reputation of the scientists, their universities, and their national funding agencies. In science, reputation is everything. It influences funding decisions, attracts talented students and researchers, and determines who gets invited to collaborate on major international projects. By demonstrating their ability to secure world-class data and produce cutting-edge analysis on a major astronomical event, Chinese institutions elevated their standing within the global scientific community. It was a powerful signal that they were not just participants, but leaders in the field. This helps to build what is often called scientific capital, a form of influence and prestige that can be incredibly valuable. It is a bit like being the first person to solve a key clue in a complex mystery. Once you have that clue, you're in the best position to figure out the next step in the investigation. You can lead the way, and others will naturally follow your line of reasoning. The Chinese images were a major clue in the mystery of 3I Atlas, and by finding it first, the Chinese scientific community was positioned to lead the next phase of the investigation. This is not to say that their interpretation would be the only one or that it could not be challenged. Science is a self-correcting process, and all findings are subject to peer review and further scrutiny. However, there is an undeniable and powerful advantage that comes from being the first to put a new, important piece of the puzzle on the table. They were no longer just commenting on data collected by others, they were providing the primary data that everyone else needed to work with, fundamentally changing their role in the global conversation. The drama surrounding the observation of Comet 3I Atlas pulls back the curtain on a deeper and more complex issue in modern science: the control of data, the concept of scientific sovereignty, and the powerful geopolitical implications of who discovers what in the cosmos. The journey of this single comet through our solar system has inadvertently shone a bright light on the evolving rules of a high-stakes game. Who owns the images of the stars? Who controls access to the discoveries we make about our universe? And how does this control translate into real-world influence? These are no longer simple academic questions. They are at the very heart of the future of global scientific collaboration. For many years, the unwritten rule in much of the astronomical community, particularly in the West, has been a commitment to open data. Major observatories funded by public money, such as those run by NASA or the European Southern Observatory, often have policies that make their data publicly available to any scientist in the world after a certain proprietary period, which is usually about a year. This period gives the original team that proposed the observations a chance to analyse it first. After that, the data enters a public archive, becoming a resource for the entire global community. This philosophy of open access has been a powerful engine for discovery. It allows researchers from countries with no major telescopes of their own to participate in cutting-edge science. It also means that old data can be reanalyzed with new techniques, leading to unexpected discoveries years after the fact. However, this tradition of open data is not universal, and it is not guaranteed. As new nations become major players in space science, they bring with them their own policies and philosophies about data sharing. A country like China, for instance, may choose to operate differently. It might decide to keep the data from its national observatories under tighter control, releasing it more strategically or keeping it exclusively for its own scientists for a longer period. This is not necessarily a malicious act. It can be seen as a way to maximize the return on a massive national investment. If a country spends billions of dollars to build a world-class telescope, it is understandable that it would want its own scientists to reap the primary benefits of the discoveries that telescope makes. This is a form of scientific sovereignty, the idea that a nation has the right to control the scientific data produced by its own facilities. This raises profound questions about fairness and the spirit of scientific inquiry. Is a discovery made about a comet that is passing through our shared solar system the property of the nation whose telescope happened to be pointing at it? Or does that knowledge belong to all of humanity? There is no easy answer to this question, and different countries may come to different conclusions. The 3I Atlas event brought this simmering debate to the forefront. When China released its images, it was a positive contribution, but it also served as a reminder that they were in control of that data. They chose when to release it and what to release. This power to control the flow of information is a significant form of leverage. Controlling access to crucial scientific data can be a form of soft power, a way for a country to exert influence on the world stage without using military or economic force. By becoming an indispensable source of information, a country can attract international partners who want to collaborate. It can shape the direction of research globally and ensure that its scientists are at the center of the most important conversations. For example, if Chinese telescopes are the only ones capable of tracking a potentially hazardous asteroid, then other nations will have to cooperate with China on its terms to ensure planetary defense. In this way, astronomical data becomes a strategic asset, much like control over a critical resource or a key shipping lane. The 3i Atlas episode demonstrated this principle in action. For a brief period, the world's understanding of this unique interstellar object was dependent on the data released by China. This gave them immense influence over the scientific narrative. It also showcased the potential risks of a world where data is not always openly shared. If data is held back or released selectively, it could slow down the overall pace of scientific progress. It could lead to a fragmented scientific community where researchers in different countries are working with different sets of information, unable to collaborate effectively to get a complete picture. The story of this one comet has therefore become a case study in the complex interplay between science, politics, and national interest. It challenges the entire scientific community to think deeply about the rules of the road for the next era of discovery, an era in which the cast of players is larger, and the question of who controls our discoveries is more important than ever. The successful observation of Comet 3i Atlas at a critical moment was more than just a scientific achievement for China. It was a powerful moment of national pride and a significant boost to its international standing. For decades, China has been methodically and ambitiously investing in its scientific and technological capabilities, with a particular focus on its space program. This effort is not just about pure science, it is deeply intertwined with national identity, global prestige, and the country's vision of itself as a leading power in the 21st century. The release of the Comet images, perfectly timed to fill a gap left by the West, served as a stunning global showcase of this investment, a moment where China's progress was undeniably on display for the entire world to see. China's journey in space exploration has been one of rapid and impressive ascent. The country has poured enormous resources into developing its space infrastructure, from powerful Long March rockets to a growing network of satellites. This investment has led to a string of remarkable achievements that have captured the world's attention. They have successfully sent astronauts, or taikonauts, into orbit, built their own space station, Tiangong, and executed a series of highly successful robotic missions to the Moon. Their Chang'e program, for example, achieved a historic first by landing a rover on the far side of the Moon, a technically challenging feat that no other nation had ever accomplished. They have also sent a rover to Mars, joining the United States as only the second country to operate a long-term mission on the Martian surface. These high-profile missions are a source of immense national pride within China. They are celebrated in state media and are seen by the Chinese public as tangible proof of the nation's technological prowess and its return to a position of global leadership. However, deep space astronomy and the study of objects like comets and asteroids represent a different, more subtle frontier. While perhaps not as publicly thrilling as landing on another world, building world-class observatories and contributing fundamental knowledge about the universe is a key indicator of a nation's scientific maturity. It shows a commitment not just to engineering marvels, but to the pure pursuit of knowledge. Releasing the key images of 3i Atlas when Western telescopes were down was, in this context, a perfectly executed demonstration of China's technical power in this crucial area. It was a clear signal that their capabilities are not limited to missions within our solar system's gravitational well. They now possess the ground-based infrastructure to participate in, and even lead the observation of transient, fast-moving astronomical events. This achievement helps to shift the global perception of China's role in science. It positions the country not just as a follower or a fast learner, but as an innovator and a leader, capable of making unique and critical contributions that others cannot. This success profoundly enhances China's image as a leader in space exploration and science. Leadership in the 21st century is not just defined by economic output or military strength, it is also about scientific and technological influence. By becoming a key player in astronomy, China diversifies its portfolio of global leadership. It can now convene international conferences, lead major collaborative projects, and attract the world's top scientific talent to its institutions. This event, though centered on a single comet, becomes a powerful piece of public diplomacy. It presents a positive, forward-looking image of China to the world, a nation engaged in the peaceful and noble pursuit of understanding the cosmos. This can have a tangible impact on how people around the world, from school children to policymakers, view China's role in the world. When they read news about the latest discoveries in space, they will increasingly see the names of Chinese scientists and observatories. This normalizes the idea of China as a scientific superpower. It builds a reputation for competence and reliability. In the long run, this soft power can be incredibly valuable, fostering goodwill and creating a foundation for stronger international partnerships, not just in science, but in other fields as well. The story of 3i Atlas, therefore, became a vessel for a much larger narrative about China's rise. The light from a distant alien comet was reflected back onto Earth, illuminating a significant shift in the global landscape of power and prestige. The sudden inability of major Western telescopes to track Comet 3i Atlas, and the subsequent emergence of China as the primary source of new data, does more than just highlight a geopolitical shift. It reveals a fundamental and perhaps dangerous weakness in the world's astronomy infrastructure. For a very long time, the field has been heavily concentrated, with a majority of the largest telescopes and the bulk of the funding for astronomical research located in a small number of Western countries. This incident serves as a stark reminder that relying on just a few key facilities, no matter how powerful they are, can be a risky strategy. It underscores the critical need for a more diverse, resilient, and geographically distributed network of observatories to watch over our skies. For most of the 20th century and the beginning of the 21st, the story of big astronomy was centered on places like the mountains of California, the high deserts of Chile, and the volcanic peaks of Hawaii. These locations were chosen for their excellent atmospheric conditions, clear, stable air with minimal light pollution. Nations like the United States and countries within the European Union invested heavily in building massive observatories in these prime locations. This concentration of resources led to a golden age of discovery, but it also created an imbalance. The vast majority of the world's premier astronomical eyes were clustered in a few specific regions and controlled by a handful of organizations. This concentration creates several points of vulnerability, as the 3i Atlas event so clearly demonstrated. The first and most obvious risk is coordinated downtime. As we saw, if several of these key telescopes go offline for maintenance at the same time, or if they are all booked for other projects, it creates a significant blind spot in our global coverage. This is not the only risk, however. A single localized event could potentially disable a large portion of our astronomical capability. For example, a major political crisis, a natural disaster like an earthquake or volcanic eruption, or even something as simple as a regional power outage in a place like Chile or Hawaii could simultaneously incapacitate multiple major observatories. This would leave us vulnerable, unable to track a potentially hazardous asteroid or observe a rare, fleeting event like a supernova. Relying on a few powerful telescopes also creates a bottleneck for scientific progress. The demand for time on these instruments far outstrips the supply. This means many excellent and important scientific projects may never get approved, not because they lack merit, but simply because there are not enough hours in the night to accommodate them all. This can slow the overall pace of discovery and may discourage young scientists from entering the field. A more distributed network of observatories would create more opportunities for more scientists to conduct their research, fostering a more vibrant and competitive scientific ecosystem around the globe. The 3i Atlas incident is a powerful argument for diversifying our global portfolio of astronomical assets. It is a reminder that we need more world-class observatories spread across the entire planet, not just in a few select locations. This means investing in and building new facilities in regions that have historically been underrepresented in the field, such as other parts of Asia, Africa, and South America. Doing so would not only make our global network more resilient to disruptions, but would also bring new perspectives and talents into the scientific community. It would transform astronomy into a more truly global enterprise. This event, therefore, acts as a wake-up call. It highlights the fragility of our current system for stargazing. We have built magnificent, powerful cathedrals of science, but we have built too few of them, and we have built them too close together. The lesson from 3i Atlas is that the future of astronomy cannot be reliant on a single country or a single set of observatories. To ensure that we never again miss a critical cosmic event simply because a few key instruments are unavailable, we must build a more robust and geographically balanced network. The goal is to create a system where the eyes on the sky are always open, somewhere in the world, ready to catch the next visitor that comes wandering in from the interstellar darkness. The comet has shown us not only a secret from another star, but also a weakness in our own planetary defences against ignorance. The whirlwind of events surrounding Comet 3I Atlas has provided the global scientific community with a valuable, if somewhat stressful, fire drill. It has underscored the urgent need for a more coordinated and robust system for observing rare, fast-moving cosmic objects. The next interstellar visitor will inevitably arrive, and when it does, we need to be better prepared. This means having more than just powerful telescopes. It requires a comprehensive global strategy involving diverse instruments, rapid alert systems, and pre-planned collaborative efforts. The experience with 3I Atlas has moved the conversation about cosmic readiness from a theoretical exercise to an immediate and practical necessity. The first step in preparing for the next visitor is ensuring we have comprehensive observational coverage. This is not just about having more telescopes, it's about having many different types of telescopes in many different places. A single telescope, no matter how large, can only see a small patch of the sky at any one time and is limited to observing specific kinds of light. To get a complete picture of an object like an interstellar comet, we need a multi-wavelength approach. This means observing it simultaneously in visible light, infrared, ultraviolet, radio, and even X-rays. Each part of the light spectrum reveals different information about the object's composition, temperature, and physical processes. For instance, radio telescopes can detect certain molecules that are invisible to optical telescopes, while X-ray observatories can spot high-energy interactions with the solar wind. This requires a global network of different facilities working in concert. We need large optical and infrared telescopes on the ground for high-resolution imaging and spectroscopy. We need space-based observatories like Hubble and JWST for their clarity and unique wavelength capabilities. And we need a global array of radio telescopes to listen for the faint whispers of complex molecules. The lesson from 3I Atlas is that we cannot afford for any major component of this network to be down at a critical moment. We must build more redundancy into the system. This leads to the need for designated backup observatories and better global alert systems. When a potentially interstellar object is first detected by survey telescopes like Pan-STARRS or the upcoming Vera C. Rubin Observatory, an alert needs to go out instantly to the entire world. This alert should trigger a pre-planned protocol, a set of instructions that helps to coordinate the global response. This protocol could include a list of designated observatories around the world that have agreed to devote a certain amount of target of opportunity time to these events. Having this system in place beforehand would eliminate the scramble to get telescope time and ensure that follow-up observations begin within hours of discovery, not days. This coordination must be truly global, breaking down old barriers between nations and institutions. The 3I Atlas event showed that scientific leadership can come from anywhere. A future global network must therefore fully integrate the capabilities of all spacefaring nations, including established players like the United States and Europe, as well as rising powers like China and India, and other countries with growing astronomical communities. This means more data sharing agreements, more joint projects, and a more collaborative spirit. The goal should be to create a system where the best instrument for a particular job is used, regardless of which country's flag is flying over the observatory. The urgency of this readiness is driven home by the nature of these interstellar objects. They are rare, giving us few chances to practice. They move incredibly fast, giving us a very short window to react, and they are often discovered when they are already on their way out of the solar system, meaning the clock is already ticking from the moment we first see them. We do not have the luxury of waiting a few weeks to organise a response. We need a system that can be activated at a moment's notice, a sort of cosmic emergency broadcast system for astronomers. This might involve using artificial intelligence to automatically flag potential interstellar candidates, and even schedule preliminary follow-up observations on robotic telescopes, all before a human scientist has even had their morning coffee. Ultimately, the story of 3I Atlas is a powerful motivator. It has exposed weaknesses in our current approach, but has also shown what is possible when new facilities come online. It has given the astronomical community a clear mandate: work together to build a more resilient and comprehensive skywatching system. The next visitor from another star is out there, silently travelling through the void heading our way. Whether we are ready to greet it and unlock its secrets depends entirely on the lessons we learn and the actions we take today. The Comet has served as a cosmic messenger, and its message is simple: be prepared. While the new images of Comet 3i Atlas from China were a welcome and crucial contribution to science, their arrival also prompted a series of important and critical questions from the broader astronomical community. When data from a new instrument or a different observatory is introduced into a global scientific effort, it is not enough for the pictures to simply look good. For the data to be truly useful and trustworthy, it must be carefully vetted and understood. Scientists immediately began to ask pointed questions about the technical details of the Chinese data, focusing on issues of calibration, access to raw information, and the potential for misinterpretation without the full context from other observatories. The first and most fundamental question revolves around calibration. Calibration is the process of ensuring that measurements from one telescope can be accurately and reliably compared to measurements from another. It is a cornerstone of collaborative science. Imagine two people trying to measure the length of a table, but one is using a ruler with inches and the other is using a ruler with centimeters. Unless they carefully convert their measurements to a common unit, their results will not make sense when compared. The same principle applies to telescopes. Each telescope and each camera has its own unique characteristics. The way its detectors respond to light of different colors and brightnesses must be precisely measured and accounted for. This process allows astronomers to convert the raw pixel values in an image into scientifically meaningful units, such as brightness or energy flux. So, when the Chinese images appeared, scientists around the world began to ask, how are these images calibrated? Were the methods used consistent with the standards used by other major observatories, like the VLT or the Hubble Space Telescope? Without this information, it is difficult to combine the Chinese data with the data sets from other facilities to create a single, consistent timeline of the comet's behavior. A simple change in brightness seen in the images could be a real event happening on the comet, or it could just be an artifact of a different calibration process. To resolve this, the observing team must publish detailed information about their methods, a process that is standard practice in the scientific community, but one that requires time and transparency. A related and equally important issue is the access to raw data. The beautiful astronomical images we see in the news are almost always highly processed. The original unprocessed images that come directly from the telescope's detectors are known as raw data. These files contain the pure, untouched measurements of light, along with a wealth of metadata, information about the exact time the image was taken, the filters used, the telescope's pointing direction, and the instrument's temperature. For other scientists to independently verify a result, they need access to this raw data. It allows them to perform their own calibrations and analysis, checking the work of the original team and ensuring that the conclusions are sound. Therefore, a key question for the Chinese institutions was, will the global community be allowed to access the raw data files? A willingness to share raw data is often seen as a litmus test for commitment to scientific openness and transparency. If access is restricted, it can lead to skepticism, as other researchers cannot fully replicate the analysis. They are forced to simply trust the processed images and the conclusions of the team that released them. While there may be valid national policy reasons for controlling data, in the world of pure science, open access to raw data is the gold standard that fosters trust and accelerates progress. Finally, there is always a risk of overinterpreting limited data, especially when it comes from a single source during a period when no other telescopes are providing confirmation. If only one observatory reports a strange new feature, for example, a sudden jet of dust erupting from the comet's nucleus, scientists will be cautious. Is the feature real, or could it be an instrumental glitch, an artifact of the image processing, or a cosmic ray hitting the detector? The best way to confirm a discovery is to have it independently observed by a different telescope. Since the Chinese images came during a gap in Western observations, this kind of immediate independent verification was not possible. This does not mean the data is wrong, but it does mean that scientists must be extra careful in their interpretation. To help with this, it is crucial for the observing team to share all the important details. This includes the exact instrument settings, the precise times of each observation down to the second, and a full description of the weather conditions and sky quality at the time, all of these factors can affect the final image. Without this complete context, the risk of misinterpreting a subtle feature increases. These critical questions are not an expression of distrust, but rather a reflection of the rigorous, self-skeptical nature of the scientific process itself. Before a new piece of evidence can be fully accepted, it must pass a thorough and demanding cross-examination. The sudden data gap and China's dramatic intervention in the observation of 3I Atlas has served as a profound and necessary wake-up call for the entire global astronomical community. This single event, centered on one fleeting comet, has exposed the hidden fragility of our global system for monitoring the cosmos. It has forced a critical re-evaluation of long-held assumptions and sparked an urgent conversation about the need to build a more diversified, equitable, and resilient network for watching the sky. The key takeaway is clear: the future of astronomy cannot and should not be dominated by any single country or a small consortium of nations. True progress and security will only come from a truly global effort. For decades, the unstated reality of astronomy was that a handful of powerful players set the agenda. The institutions with the biggest telescopes and the largest budgets naturally led the charge on the most exciting discoveries. While this model produced incredible science, the 3I Atlas incident revealed its inherent weakness. The astronomy community now realizes, perhaps more clearly than ever before, that putting too many of our observational eggs in one basket is a risky proposition. The incident demonstrated that no single set of telescopes, no matter how advanced, should have a monopoly on our view of the universe. When that single viewpoint is obscured, whether by maintenance, weather, or scheduling conflicts, our collective vision suffers. This realization is driving a powerful new push for greater diversification in our astronomical infrastructure. This means moving beyond the traditional centers of power and actively investing in and supporting the development of world-class observatories in more parts of the world. There is a growing consensus that we need more major facilities in places that have been historically underrepresented in the field, such as across the continents of Asia, Africa, and South America. Building powerful telescopes in these regions is not just a matter of fairness or equity. It is a strategic necessity for the health and robustness of the science. It would distribute our capabilities, making the global network far less vulnerable to localized disruptions. This shift in thinking requires a change in how major funding projects are conceived and supported. Instead of focusing solely on building the next single biggest telescope, funding agencies in Europe and North America may need to dedicate more resources to projects that support international partnerships and help build capacity in developing nations. This could involve co-funding telescopes in new locations, establishing programs for instrument development with new partner universities, or investing in the data infrastructure needed to connect a more distributed network of observatories. The goal is to create a multipolar world of astronomy where cutting-edge discovery can happen anywhere. The ultimate vision is a global system that is more than the sum of its parts, a network of observatories that are deeply interconnected, sharing data, and coordinating observations in real time. This would create a resilient web of telescopes, rather than the current model which looks more like a few large isolated islands. In this future system, if a telescope in Chile goes down for maintenance, a partner telescope in, for example, Southern Africa or Western Australia, could seamlessly pick up the observational duties. This would ensure the kind of continuous, 24/7 coverage that is essential for studying transient events like supernova, gamma-ray bursts, and of course, interstellar visitors. The 3I Atlas event has provided the perfect catalyst for this change. It is a concrete, high-profile example that everyone in the field can point to when making the case for a new, more global approach. It has moved the discussion from abstract principles to practical realities. The astronomy community now has a shared story that illustrates the danger of the old model and the promise of a new one. The goal now is to harness the momentum from this wake-up call and turn it into tangible action, new funding, new partnerships, and a new global architecture for discovery. In this way, a single comet's journey has done more than just teach us about another star system. It has forced us to rethink how we, as a unified planet, should watch over our own cosmic shores. How China chooses to handle this moment, its moment in the astronomical spotlight, could have a lasting impact on its global reputation and its role in the future of space science. This is more than just a single discovery. It is a critical test of scientific leadership. If China manages this situation with transparency, collaboration, and a spirit of open inquiry, it could solidify its position as a key and welcome partner in the global scientific enterprise. This could reshape the landscape of international partnerships for decades to come, opening the door to new and ambitious collaborative projects. The way it navigates this opportunity will send a powerful message to the world about its intentions and its vision for the future of space exploration. If China fully embraces the traditions of open science, the potential for positive outcomes is enormous. This would involve publishing its results in peer-reviewed international journals, presenting its findings at major astronomical conferences, and most importantly, making its raw data fully and easily accessible to any researcher in the world through public archives. This level of transparency would allow scientists everywhere to verify the findings, build upon the work, and integrate the Chinese data seamlessly with their own. By doing so, China would demonstrate a commitment not just to its own national scientific advancement, but to the advancement of human knowledge as a whole. This would build an immense amount of trust and goodwill within the international community. This moment could serve to redefine how China collaborates with other countries on major space projects. In the past, some of its most ambitious missions have been largely national efforts with limited international participation. A successful and open collaboration on the science of 3i Atlas could serve as a model for the future. It could lead to deeper partnerships with NASA, the European Space Agency, and other major players. Imagine future missions to the outer planets, or the construction of the next generation of giant telescopes being conceived from the start as true global partnerships, with China as a founding and equal member. This would allow for more ambitious projects than any single nation could undertake on its own, pooling resources, expertise, and technology to tackle the biggest questions in science. The success and positive reception of the 3i Atlas observations could directly lead to more international collaborations in the future. Scientists and funding agencies in other countries would see Chinese institutions as reliable and valuable partners. This could smooth the path for Chinese scientists to get more involved in existing international projects, and for international scientists to gain access to China's unique and powerful facilities, such as their fast radio telescope, the largest single-dish instrument in the world. This would create a virtuous cycle of collaboration, where shared success breeds more shared projects, ultimately accelerating the pace of discovery for everyone. This is a genuine opportunity for China to demonstrate true scientific leadership. Leadership is not just about having the best hardware or making the first discovery. It is also about fostering a healthy, open, and collaborative environment where science can flourish. By championing these values, China can help to shape the norms and standards for the next era of global science. This would be a powerful form of soft power, earning the country respect and admiration for its contributions to a shared human endeavour. It would be a transition from simply being a nation with advanced technology to being a nation that is a trusted steward of scientific progress. Of course, there is another path. If the data is kept proprietary, if collaboration is limited, and if the focus remains primarily on national prestige, the opportunity could be squandered. This would likely breed suspicion and mistrust, reinforcing divisions within the scientific community and making future partnerships more difficult. The choice of which path to take lies with China's scientific and political leadership. The global community is watching closely. The way this story unfolds will be a powerful indicator of how the new, multipolar world of science will operate. This single comet, a random visitor from the void, has presented China with a historic opportunity to help define the future of how humanity works together to explore the universe. The sudden prominence of Chinese observatories in the 3i Atlas story is likely to provoke a significant reaction from Western astronomical institutions. This event serves as a Sputnik moment for the field, a surprising demonstration of a competitor's capability that will surely spur action. Faced with this new reality, Western observatories and their funding agencies will likely respond by adapting their strategies in several key areas. They may accelerate planned upgrades, push harder for the development of more distributed and resilient telescope networks, or even seek to form new strategic alliances to ensure they remain at the forefront of discovery. This is not just about competition, it is about adapting to a new and more complex sky. One of the most immediate and practical responses will likely be an acceleration of planned maintenance schedules and technology upgrades. The fact that several major telescopes were offline at such a crucial time will be seen as a lesson learned. Observatory directors and funding bodies will likely re-examine their schedules to see if they can be made more flexible or if critical maintenance can be done more quickly. There may also be a renewed push to secure funding for next-generation instruments and detector upgrades to ensure their facilities maintain a competitive edge. The goal will be to minimize downtime and maximize the scientific output of these multi-billion-dollar investments. Beyond individual facility upgrades, this event will add powerful momentum to the argument for building more distributed telescope networks. Scientists have been advocating for this for years, but the 3i Atlas incident provides a perfect high-profile case study to support their cause. We are likely to see increased lobbying and support for projects that involve linking multiple telescopes across different continents. This could mean strengthening existing networks or investing in new, smaller, robotic telescopes that can be deployed quickly and cheaply in many locations. The idea is to move away from relying on a few super telescopes and toward a more integrated system where many observatories work together as a single, global instrument. This would make the overall system far more resilient to the kinds of disruptions that affected the 3i Atlas observations. This push for distributed networks may also lead to new and reconfigured international partnerships. Western institutions might actively seek out new alliances with observatories in countries they have not traditionally partnered with, in an effort to fill geographical or capability gaps in their coverage. For example, they might form new agreements with observatories in India, South Africa, or Australia to ensure better 24-hour coverage of the sky. The goal is to build a more robust and collaborative global team, ensuring that if one partner's facilities are down, another can step in. This is a strategic adaptation, recognizing that in this new environment, collaboration is a key to maintaining leadership. Furthermore, this event could provide the political will needed to fund more comprehensive backup systems and rapid response capabilities. This might include dedicating more resources to all-sky survey telescopes, whose primary job is to scan the skies every night, acting as a cosmic alarm system. It could also mean creating dedicated funds that can be accessed quickly to buy observation time on a wider range of telescopes, including private or commercially operated ones, in the event of an urgent astronomical discovery. This would be like having an emergency response fund that allows scientists to bypass the normal, slow-moving process of applying for telescope time when a truly unique event occurs. In essence, the Western astronomical community is being forced to adapt to a new, more competitive environment. For decades, they were the undisputed leaders, setting the pace of discovery. The 3i Atlas event has shown that they now have a serious and capable peer in China. The response will not be one of simple retreat, but rather one of innovation and strategic adaptation. They will likely work to make their own systems more efficient and resilient, while also seeking out new partnerships to build a more robust global network. This competition, if it remains healthy and focused on scientific goals, could ultimately be a very good thing for astronomy. It will push everyone to be better, faster, and more collaborative, accelerating the pace of discovery for all of humanity. The sky is now being watched by more eyes than ever before, and the race to understand its secrets has become more dynamic and interesting. Amid all this human drama, the competition between nations, the debates over data, and the strategic maneuvering of scientific institutions, it is easy to forget the central character of our story, the comet itself. Comet 3i Atlas is completely indifferent to our earthly politics. It does not care which telescope is watching it, which country's flag flies over the observatory, or who gets to publish the first scientific paper. It is a silent, ancient traveller, a physical piece of another solar system, executing a lonely journey governed only by the fundamental laws of gravity and physics. Its passage through our solar system is a brief, singular event, a fleeting moment in a journey that has lasted for millions of years and will continue for millions more. This perspective adds a poetic and humbling dimension to the entire affair. The comet is a messenger carrying secrets from a star that is likely thousands of light years away. It is a time capsule from a place and a time that we can barely imagine. The chemical makeup of its frozen core tells a story about the cloud of gas and dust from which it was born, a story that is completely alien to our own. It is a silent witness to the formation of another family of planets around another sun. It travels through the vast, cold emptiness between the stars, a journey of unimaginable scale and duration. And for a brief moment, its path happens to intersect with our own small, brightly lit corner of the galaxy. This makes every observation, every picture, and every piece of data we collect an absolutely unique and irreplaceable treasure. Because 3i Atlas is on an unbound trajectory, it will never return. This is not like Halley's Comet, which visits us every 76 years. This is a one-time performance. We have a short, precious window to learn everything we can from this cosmic visitor before it recedes back into the interstellar darkness, eventually becoming too faint for even our most powerful telescopes to see. Once it is gone forever. The opportunity to study this specific object will be lost to all future generations of humanity. This non-repeatable nature of the observation is what gives the scientific endeavour its sense of urgency and profound importance. It elevates the work of the astronomers beyond mere data collection and turns it into an act of preservation. They are like cosmic archivists, carefully recording the details of a visitor who will never pass this way again. Each photon of light collected by a telescope's mirror is a piece of a story that can never be retold. Every spectrum that reveals the comet's chemical fingerprint is a unique glimpse into the building blocks of another world. This cosmic perspective helps to put our human dramas into context. The race for prestige and the competition for funding are, in the grand scheme of things, secondary to the magnificent and humbling opportunity that stands before us. The comet reminds us that we are all inhabitants of a very small island in a vast cosmic ocean, and a message in a bottle from another shore has just washed up. The most important thing is not who found the bottle first, but that we all work together to decipher its message before the tide comes and washes it away forever. This moment calls for our best selves, for collaboration, for openness, and for a shared sense of wonder. The comet itself is an ambassador from the wider galaxy, and its brief visit is a powerful reminder of how much there is still to discover, and how we are all in this quest for knowledge together. The story of Comet 3i Atlas is ultimately much larger than the story of a single strange piece of ice and rock. Its brief passage through our solar system has served as a catalyst, illuminating and accelerating a fundamental shift in how humanity observes the universe, who gets to lead in making new discoveries, and what the future of global scientific collaboration will look like. This event is a landmark not just for astronomy, but for the history of science itself. It signals the dawn of a new era of discovery, one that will be more global, more competitive, and more complex than ever before. For the first time in the modern era of astronomy, this event has fundamentally changed who watches the skies and who makes the big discoveries. The narrative of cosmic exploration is no longer being written exclusively by a small club of Western nations. The emergence of China as a key player, capable of providing critical data when others could not, marks a permanent change in the landscape. This is not a temporary anomaly. It is the new reality. The map of scientific power has been redrawn. Discoveries will now come from new places, driven by new investments and new perspectives. This diversification is a sign of a maturing global scientific community, where excellence is distributed more broadly across the planet. As a result, the future of space science will almost certainly involve more shared work and a greater emphasis on true international collaboration. As more nations develop advanced capabilities, the model of a single country going it alone on major projects will become less feasible and less desirable. The most ambitious projects of the future, whether it's building a telescope on the moon or sending a mission to another star, will be so complex and so expensive that they will require the combined resources and expertise of multiple international partners. The 3i Atlas event, by highlighting both the strengths and weaknesses of our current systems, will act as a powerful argument for creating these deeper, more integrated global partnerships. This moment is, above all, a testament to humanity's shared and enduring curiosity. The comet, an object of no practical or economic value, captured the attention of people all over the world. It did so because it speaks to a fundamental human desire to explore, to understand our place in the universe, and to know what lies beyond the horizon. This curiosity knows no national borders. The questions that 3i Atlas raises about the formation of planets, the diversity of other star systems, and the ingredients for life are questions that unite us as a species. They remind us that for all our differences here on Earth, We share a common home in the cosmos and a common drive to understand it. Ultimately, the great lesson of Comet 3i Atlas is that discovery belongs to all who are ready and willing to look up. It is not the birthright of any single nation or culture. It is a reward for investment, for dedication, for careful planning, and for the patient pursuit of knowledge. The comet's journey has shown us that the sky's open to everyone with the tools and the ambition to explore it. As we move forward into this new era, the story of this strange visitor from another star will be remembered as the moment when our view of the universe and of ourselves became bigger, wider, and more full of possibility than ever before. These images might be just data, or they might be the beginning of something far greater. What do you think they mean for space discovery? Share your thoughts and subscribe to keep exploring the unknown with us.